Okay, hi everyone. We're going to go ahead and get started. Welcome to this semester's first iteration of the ITC Colloquium. And today we are very happy to have Viraj Pandya visiting us from Columbia University. Viraj did his undergrad at Rutgers, where he got his degree in math and economics with a minor in astronomy. He then did a post-bac program at Princeton in astrophysics before moving on to get his PhD at UC Santa Cruz. And during that time, he also spent some time as a predoctoral fellow at the Center for Computational Astrophysics at the Flatiron Institute in New York. And now he is a Hubble Fellow at Columbia University, and he works on all sorts of interesting problems in galaxy evolution, both theoretically and observationally, and is today going to tell us about galaxies going bananas. So welcome very much, Viraj, and I'll let you take it away.
Okay, thank you so much for the invitation and for hosting me, and thanks in particular to Avi Loeb for also the invitation and for many insightful discussions about this exciting science. So in this talk, I'm going to try to convince you that there is an important unsolved puzzle concerning the 3D shapes of high-redshift star-forming galaxies, including Milky Way progenitors. This is based on work in a recently accepted paper entitled Galaxies Going Bananas. I promise by the end of this talk, you will all be convinced that Galaxies Going Bananas is an accurate description of our results. So this is work done in collaboration with Haowen Zhang, a finishing grad student at the University of Arizona, Mark Huerta's company, Karthik Iyer, another Hubble Fellow at Columbia, Liz McGrath, Steve Finkelstein, who is the PI of the JWST CEERS collaboration that I'm a member of, as well as the developers of the source extracted ++ code. So here is a brief outline. So I'll start with a brief review of the history of the problem, before then presenting our new results from JWST, and then talking about some implications for galaxy formation. And then at the end, I'll say a few words about where we think the field has to go from here to follow up on these results. So this is going to be about a 30 to 40 minute talk. I'm happy to take questions during it, and also with the extended discussion afterwards. So I'd like to start with this quote from Edwin Hubble's APJ article from almost 100 years ago, where he says that nearby galaxies, there are many more galaxies nearby that appear round or nearly round in projection than can be accounted for by randomly oriented disk-shaped objects alone. And so as we know, this is one of the basic galaxy properties, the ellipticities in projection, that Edwin Hubble used to justify his development of the Hubble sequence or the Hubble tuning fork diagram, where he suggested that there actually are these intrinsically spheroidal elliptical galaxies in the nearby universe. And of course, today we take it for granted, I think, but it really took decades of work by many astronomers to establish that at least at low redshift, this Hubble sequence is actually also a 3D geometry sequence, in the sense that maybe some of the most massive ellipticals on the left here are truly round in 3D, and as you move towards the spirals, you're looking at flattened pancake structures in 3D. So of course, many years later, the telescope named after him made many great discoveries, and one of the most exciting, in my opinion, is that with some of the first Hubble deep fields, many astronomers found these very elongated and clumpy star-forming galaxies at high redshift that they called chain galaxies. You can see some examples here. So many astronomers followed up on this, including, there's a nice paper by the Elmegreens in the mid-2000s, where the title just nicely explains the result. As you look closer to the detection limit of Hubble imaging at the time, you start to get dominated by lots and lots of linear-looking galactic structures. There's a nice paper by Swarup Ravindranath, also in the mid-2000s, who quantified the projected ellipticity distribution of high-redshift star-forming galaxies, showing that many of these early galaxies are biased towards having elongated axis ratios in projection. And this is very different from the distribution of ellipticities of nearby star-forming galaxies, which is relatively uniform. So all this early work was using some of the earlier instruments on Hubble. So there were always concerns that you're probing the rest frame UV optical morphology of these early galaxies, and maybe that's a biased tracer of the underlying bulk geometry of these high redshift systems. And so with the advent of the wide field camera 3, which could look at near infrared wavelengths and therefore the rest frame optical morphology of high redshift galaxies, and the completion of major surveys with Hubble, like candles and 3D HST, there's a nice paper by Ari and van der Wel in 2014, which showed that in the rest frame optical with much larger sample sizes, high redshift star-forming low-mass galaxies do indeed have projected axis ratio distributions that are very asymmetric and skewed towards edge-on values, like B over A peaking at 0.3 to 0.4. And this is very different from the axis ratio distribution of low redshift star-forming dwarfs, which is not biased towards elongated values. And it's also very different from the axis ratio distributions of massive star-forming galaxies at any redshift that Hubble could probe, which is also not biased towards elongated values and instead is relatively uniform. So there's lots of explanations that were proposed for this puzzle. And probably the original, maybe one of the most safest ones, is to say, well, okay, we do see low surface brightness disks in the local universe. And maybe we're seeing lots and lots of these elongated systems at high redshift because those are easier to detect and you're just not seeing the face-on rounder objects. And there were simulations that came afterwards that bolstered these claims, where in these simulations it was predicted that high redshift star-forming galaxies would be intrinsically clumpy, possibly, and then you would be more likely to observe one of these things edge-on when it would look like a chain galaxy, and less likely to observe it face-on, when it would have a lower surface brightness, as Avi has also recently reminded us. So this is one side of the argument. Okay, there's another side of the argument, another camp that says that no, there actually might be some intrinsic 3D geometrical evolution in the galaxy population as you go towards higher redshift and lower masses, in the sense that high redshift star-forming low-mass galaxies are not simply axisymmetric disks. Instead, they're significantly flattened along a second axis, so that many of them in 3D are shaped like cigars, these prolate ellipsoids, or like surfboards, these triaxial ellipsoids or oval disks as opposed to circular disks. So this sounds very exotic, and some of you might be wondering, well, actually, I know what those things are. We see those things in the local universe, these very heavily flattened objects. Maybe these things are just bars, right? So that's tempting, but we don't see any hint usually of a very bright, aka massive, underlying self-gravitating stellar disk. So you can think of these as bars if you'd like, but the way that they form might be very different from the bars that form in local massive disks due to secular bar instabilities, for example. So what is another way to form these kinds of elongated structures? Well, there actually are cosmological simulations that predict the existence of these elongated galaxies in the standard lambda CDM cosmology and very reasonable baryonic physics prescriptions. And the story from these cosmological simulations is that the galaxies that are elongated at high redshift and low masses, they live in dark matter halos that are themselves elongated in the same direction. And this entire system lives in a dark matter filament in the cosmic web, and that filament dictates the flow of gas and mergers along a preferential direction and leading to these elongated shapes. So if this is true, I wrote a paper in 2019 suggesting that we actually might expect to see strong intrinsic alignment signals for these high redshift elongated galaxies if they're tracing out filaments of the cosmic web. So I think this is going to make a comeback in the next few years with the launch of the Roman Space Telescope, as I'll tell you about in a couple minutes. But in the meantime, I want to just take a second and pause and say that it's been 30 years since Hubble first discovered these very elongated high redshift star-forming systems, and I would argue that we don't have a definitive explanation for this observational puzzle. So I got very excited because, as we know, a few years ago, JWST was launched, and there were lots and lots of very exciting and cool papers, for example, by Dan Eisenstein, which showed very convincingly that in cases where Hubble had missed obvious disks, JWST picks them up with relative ease, right? So beautiful stuff. Beautiful work also by Brant Robertson showing that JWST, you could identify many more disk-like objects in JWST imaging that were missed by Hubble. And then my favorite plot of 2022 is probably this one by Ferreira et al., which plots the disk fraction detected in HST as a function of redshift. You can see it's dropping dramatically, but then the disk fraction in JWST is much larger at the 40 to 60% level. So very interesting. So I got excited. I thought this is it. JWST has solved the 3D geometry crisis. It's detected all the round face-on projections of circular disks, and we're done. But then we started to ask this question, like, all this stuff actually begs the question, what do you mean by a disk, right? So usually the way that you identify disks in imaging is you use visual classifications of individual galaxies one at a time, or you look for exponentially decaying surface brightness profiles like we observe for local galactic disks. But these are necessary but not necessarily sufficient conditions for saying that something is definitively a disk. And so we went in, we wanted to do follow-up analysis on this, and I'm part of one of the JWST early release science collaborations known as CEERS. Here's me as a first-year grad student at Santa Cruz, very excited, contributing to the proposal writing process and shadowing the PI, Steve Finkelstein, as he was putting together this amazing 100-person plus collaboration. So the CEERS team and I went in, and we essentially, for the JWST multi-wavelength imaging from NIRCam, we essentially went in and we fit every galaxy with an ellipse. In detail, a surfboard-shaped model to capture the 2D light distribution, but we're effectively characterizing every galaxy by the projected axis ratio of its best fitting ellipse at the half-light radius, or a surfboard-shaped model. And then once we've done this, we're essentially doing a very simple counting experiment. We're just saying for galaxies that have fixed mass and fixed redshift that are star forming, what is the distribution of projected axis ratios? Right? So when we do this, we still find the same puzzle. With the extremely more sensitive JWST imaging, we're finding that high redshift galaxies, stellar masses that we think are consistent with them being Milky Way progenitors, in the rest frame optical, star-forming objects that we think are comfortably above the detection limit, as I'll tell you in a few slides, we are still seeing lots and lots of more edge-on systems than face-on round systems. So this is a puzzle, and we have to interpret it. But before I get to that, the title of the paper is Galaxies Going Bananas. Why do we title it that? Because we don't just look at the 1D distribution of B over A. We look at the 2D joint distribution of B over A as a function of size. And when you look at this distribution for galaxies that are preferentially at high redshift and low stellar mass, they trace out a particular shape in this diagram. So you see at a fixed mass, fixed redshift, and fixed size, galaxies at a fixed size are populating generally, they appear preferentially edge-on. There's a deficit of rounder objects. And in fact, when we made this plot, it looked to us like it was the shape of a banana, and so that is the inspiration for the title of the paper, Galaxies Going Bananas. Okay, so very exciting. Here are some images of some of these representative galaxies. They're consistently flat and elongated. Many of them are actually very clumpy, like the old HST chain galaxies. And my main point is that there are way too many of these edge-on looking systems such that if you want to preserve isotropy, you're not seeing enough of the face-on configurations, so that implies that not all of these can just be axisymmetric circular disks seen from the side. Okay? So sensational title was picked up by the New York Times. You may have seen the front page of the New York Times a few weeks ago with this paper featured on it. Very exciting stuff. Columbia did a nice YouTube video where I really leaned in the banana analogy. And then NASA did a nice press release also a few weeks ago suggesting a beach-themed analogy that galaxies are surfboards and pool noodles and frisbees and volleyballs and so on. So this is all very exciting, but as Avi reminded us, you have to be very careful in this kind of analysis because of selection effects involving surface brightness. Okay, and in particular the fact that face-on disks are harder to detect versus edge-on disks because the light is more spread out and diffuse in the former. So the way that we address this in my paper is we ask this important question: is this deficit of galaxies, round galaxies to the top right of the banana, is that deficit of round galaxies real? And the way that we address that question is we actually injected fake galaxies into the real JWST CEERS imaging over a range of surface brightnesses, combinations of magnitude and size, and axis ratios, and we quantified our detection limits of our data empirically, and we showed that if there were large face-on disks down to stellar mass 10 to the 9, the limit of our sample selection, for the typical mass-light ratios expected, we should have seen large face-on round disks in the dwarf regime and high redshift. But we didn't, and so now we have to interpret this puzzle. So what is our interpretation? So let's start by approximating galaxies as different kinds of 3D ellipsoids. I'm showing you some example extreme cases here. Spheroids on the left, oblate or axisymmetric or circular disks in the middle, and then this third class of these prolate cigar-shaped ellipsoids on the right. So if you're like me, it may be hard to imagine or visualize these things in 3D, so let me offer the definitive analogy straight from New York City. Start with a perfectly round ball of dough. In 3D, that's a spheroid. Flatten that along one axis, you get the greatest thing in the universe, pizza. Now take that pizza, flatten it along one of the other two axes, you get my other favorite thing in the entire universe, a breadstick. Okay, so this is what you should have in mind for these different kinds of simplified ellipsoids. Now, the key thing to realize is that a population of each of these kinds of ellipsoids is going to leave a unique signature on that B over A versus size diagram. So take, for example, spheroids. No matter which way you look at them, they're going to appear round or circular in projection. So on the B over A size diagram, they're going to appear near the top. Disks that are circular are different because you're equally likely to observe them from a range of viewing angles. And so you actually expect a uniform distribution of B over A or a vertical stripe in this diagram. And then this third class of prolate ellipsoids are fundamentally different. They have two short axes. So they're kind of like this clicker. You're much more likely to observe this clicker like this or like this, and very rarely you're going to see it directly down the barrel when it looks like a small circle on the sky. So a population of prolate ellipsoids is actually going to trace out this shape on this diagram, preferentially with large sizes and small or edge-on axis ratios. So does this remind anyone of a particular fruit on the right? It reminds us of a banana. And so that is, we think, the solution to the puzzle. And just to be clear, what I'm saying or proposing is that there is a new class of galaxies at a high redshift that may intrinsically be flattened along a second axis, such that they are effectively like breadsticks. So we've actually done the Bayesian modeling. I will skip through the details, but I'm happy to walk you through that during the Q&A, the discussion. But essentially what we've done is we've asked, well, what is the optimal weighted sum of these probability distribution maps in this plane for millions of different types of ellipsoids with different intrinsic axis ratios that then reproduces the observed distribution of B over A versus size. So we've done that. And then one of the most important questions that you can ask is, okay, is there any evidence of 3D geometrical evolution? So here is from some of the best fitting models from this Bayesian analysis, the distribution of 3D C over A, the short axis ratio, versus the intermediate axis ratio. And I'll start with results for one of our lower redshift, higher mass bins. And you can see that the contribution of ellipsoids to the observed population of galaxies, low redshift and high mass, is hitting up against this oblate or spheroid region. So these are, we think, the standard things that we're familiar with, the disks and spheroids and maybe some composite thereof with possibly some bulges. But as you go towards higher redshifts and lower masses, the distribution inferred in this plane starts to shift towards exotic axis ratios. So you start to see that the distribution is starting to get elongated in the intermediate axis ratio here. And as you go towards some of the higher redshifts and lower masses, the distribution peaks in this prolate or nearly prolate region. So this breadstick or cigar-shaped region. So there's clearly some transition in the 3D shapes with mass and redshift. And this is very interesting and very puzzling, because if many people have used data from the local redshift, the local universe, to infer the 3D axis ratio distributions of nearby dwarfs, and it looks nothing like this. These nearly prolate dwarfs that we see at high redshift are very rare, if at all seen, at low redshift, with the observations, from example, from Aaron Cato Fong's recent definitive analysis from Dark Energy Survey and Hyper Supreme Cam and other instruments showing that low redshift systems in the dwarf regime hit up against the spheroid or oblate corner. So very puzzling. Something else that I want to just briefly say is that as part of this analysis, we automatically get constraints on the size-mass relation of galaxies for the very first time split by 3D geometry. And so what we're finding is that these are size-mass relations on average as a function of mass at a given redshift and then increasing in redshift from left to right along the panels. And these different colored lines just show you the size-mass relations of disks in orange, nearly prolate things in blue, and you can see that the prolate things they're big. They're just as big as the disks, maybe a tiny bit smaller. And then at a fixed mass and fixed redshift, the spheroids that are star-forming are relatively small in size, which is an interesting constraint. Now, probably the key question, does this matter, right? And the question there is, how rare are these objects? So our analysis gives us fractions, the contributions of these prolate, oblate, and spheroid objects as a function of mass and redshift. So here's a nice bar chart evolution showing the redshift dependence of the prolate or nearly prolate fraction in blue, the oblate fraction in orange, and the spheroid fraction in green for two mass bins where we think we have sample sizes, we're not driven by the priors in our Bayesian analysis and so on. And you can see that above about redshift 1, especially for the lower mass bin here, the prolate things are just dominating at the 50 to 80% level. This is not a rare population. This may be the majority of high redshift star-forming galaxies. Something else I want to point out here that's a nice sanity check is that as you go towards low redshift at a fixed mass, the contribution of the axisymmetric disks is increasing. And this is interesting because it's a nice sanity check because all of these mass redshift intervals are fit independently. They don't talk to each other. And so we're seeing the buildup of the circular disk population that we know and love, that we're familiar with at lower redshifts, which is nice to see. So as a Hubble Fellow, NASA has tasked me with answering this question, this fundamental question, how do we get here? And I was very excited to see a few weeks ago that NASA also has an entire division that tries to answer the same question. It's called the Cosmic Origins Division. And so here's my take on this fundamental question. Many of us have shown that you can actually infer the stellar mass assembly history of Milky Way progenitors. And at about redshift 2, we think Milky Way progenitors had stellar masses between 10 to the 9 to 10 to the 10, and they were star forming. I just showed you that our analysis suggests that the majority of galaxies in this mass redshift range for Milky Way progenitors are maybe intrinsically prolate or something between prolate and an axisymmetric disk. So you put these two things together, I think it might imply that maybe our own Milky Way may have gone through this kind of elongated phase in the past. So now the question is, where do we go from here? So I'm going to just step through a few ideas that we're thinking about for future work. So the first thing is that there might be interesting connections to galactic archaeology, including by people here who have shown that when the Milky Way underwent its last major merger with this Gaia Sausage Enceladus galaxy at redshift 2, that the Milky Way got quite elongated. So what an interesting coincidence that we also find large fractions of elongated galaxies at these same redshifts and masses. So interesting thing to definitely follow up. Something else I mentioned earlier, so the Roman Space Telescope is going to hopefully be launched in a few years, 2026 to 2027. And I think this is going to be a beautiful new science case for Roman that I think is currently underappreciated, where Roman is going to, in a single pointing, observe 100 Hubble deep fields at once with similar sensitivity and resolution. So you can identify these elongated galaxies over huge areas of the sky and actually go back and redo my 2019 paper properly. Look for intrinsic alignment signals, look at the clustering signals for these high redshift elongated systems compared to the rest of the population. And that'll be a great test with Roman. Something else that we're thinking about is that can you develop new non-parametric morphological statistics or even AI approaches to use imaging alone to tell whether any individual galaxy may be oblate or prolate or something in between. That's going to be very challenging, but I think it'll be exciting. Dust is going to be very important, I think, because prolate galaxies have two short axes, and you're likely to see them edge on. And so if you see a prolate galaxy edge on, it has a short path length along the line of sight, so there might be less dust attenuation compared to an edge-on axisymmetric disk, which has a longer path length and therefore maybe more dust attenuation, redder colors. So that will be fruitful. But I think the most important thing in the foreseeable future to definitively settle the debate is we need constraints on the kinematics of these systems. And not just the gas kinematics, which I am leading programs to do, and I can talk about that during the discussion, but really the stellar kinematics of these high redshift elongated galaxies, because that's going to be the smoking gun. Okay, so these simulations where we see these elongated systems, they suggest that the stars in these systems are going to be on highly radially biased orbits because they constantly undergo mergers along a preferential direction. And so we know already that if you have an axisymmetric disk, the stars are going to be on circular orbits. So you expect to see an edge-on rotation curve for edge-on systems. But in these systems, if they are prolate or triaxial, you might actually expect the stars to be on these box-type orbits where they pass through the center of the system. And so this is great because nature might have given us a great way to distinguish these two scenarios, where for any individual galaxy like this, from the imaging alone, I don't think anyone here, including myself, can say this is an edge-on axisymmetric disk, this is an oval disk, or a prolate cigar, just from the imaging alone. But the stellar kinematics may be able to constrain that. And you might also get information on, are these like clumpy things part of mergers? Is this entire thing dynamically stable? What are the implications of all of this? So the problem, of course, is that this is very challenging because you have to detect the stellar continuum, not just gas emission lines. Okay, and in that continuum, you want to resolve and detect absorption features from the stars in these galaxies that then tell you about their motion, their orbits. This is very challenging because these galaxies are very faint. They're very small, of order 0.1 arc seconds in the sky. And these simulations where these elongated systems are seen, they suggest that the rotational velocities and velocity dispersion of the stars in these systems is going to be of order 60 kilometers per second or even lower. So you need high-resolution spectrographs to resolve these narrow absorption lines. But there are things that we can already start to do, and people have actually started doing, and I'm working on as well. And the simplest thing you can imagine is you go look for one of these elongated systems, and you put a single slit on it, a long slit or a slit from a multi-object spectrograph. And if you can detect the continuum, which in this example they call the hot dog galaxy by James Lowenthal, David Koo et al., they detected several stellar absorption features with Keck Elriz corresponding to redshift 2.8 for this elongated system. But then when they went in and asked, do you see any evidence of a velocity gradient along the major axis, rotational signatures in the stars, they did not see any such velocity gradient. So they concluded that this might be a thing where it looks like an edge-on disk, but it's not rotating, so it's not an edge-on rotating disk, and maybe instead it's some kind of a truly linear, perhaps filamentary source. So the problem is that we don't have a full census of these systems down to very faint magnitudes and surface brightnesses. This is one of the brightest and biggest objects. And so we're going in now and we're using archival Keck data to check what the current census is for these kinds of non-rotating edge-on things at high redshift, low masses. But I would argue that the slit spectroscopy itself is never going to be the smoking gun either, because let me remind you that people debated for decades what was the 3D geometry of local giant ellipticals. They debated that for decades because they didn't have IFU spectroscopy and stellar velocity fields along the line of sight along the entire face of these local giant ellipticals. It was only until we got IFU data from like Atlas 3D, for example, that we really started to get a coherent picture that maybe the most massive ellipticals truly are roundish in 3D, and the lower mass ellipticals are maybe an extension of the S0s and maybe kind of oblate or flattened. And so what we really need to do in the future is to get IFU constraints of the stellar kinematics along the face of these high redshift systems. And then we can start to decompose the observed kinematics with different techniques empirically, and ideally, maybe one day we'll be able to do Schwarzschild dynamical modeling, which is very hard, but it's very important, because then you can actually choose some potential, integrate various stellar orbits in that potential, and then do a weighted sum to ask what set of orbits of stars in a given potential can reproduce both the observed image of the galaxy and its velocity field. Very hard to do. But luckily, in 10 years, we'll have the ELTs, including the Giant Magellan Telescope that Harvard here is playing a big role in. And these facilities, these ELTs, are going to have the specifications that you need to actually do this kind of science in 10 years. So I am beyond excited. I wish this was going to happen tomorrow, but unfortunately, we'll have to wait for a decade. So until the ELTs come online, just to recap, what are we working on? One, as I told you, is you can still do the slit experiment. We're using archival data. We might do some of this with JWST, maybe with Keck, to ask how many high redshift elongated low mass systems do not show evidence of a velocity gradient along the major axis for the stars. We're also looking at gas kinematics and misalignments, because we do expect that axisymmetric disks that host gas disks will follow a particular trend, for example, in terms of the gas velocity dispersions as a function of the axis ratio of the stars, like this orange line, for example. So I can talk more about that in the discussion if you're interested. And we're doing isophotal analysis for some of the largest of these things. Going back to the 70s, before we can get spectra, people used to check, well, what is the incidence of isophotal twists and other interesting features in the surface brightness distribution of galaxies, because that can give you hints on the stellar orbits before you can get kinematics. And if you really want to run wild with your imagination, many of you may know that NASA is now planning the next flagship mission after Roman, called the Habitable Worlds Observatory. This is recommended by the Decadal Survey. And so NASA has actually asked me to suggest ways in which habitable worlds might be able to play a role in this kind of important science. So with this kind of 6-meter UV optical near-infrared telescope, you'll be able to see things like this. You'll have 100 parsec resolution for these redshift 2 Milky Way progenitors. And so you can really map out their intrinsic, the internal dynamics, the structures, and then pair it up with ELTs to get IFU kinematics. This is going to be amazing. And in all of this stuff, theory is going to be absolutely essential. That's the other half of my work, as Cassie said. And so I'm the PI of a large Cycle 3 legacy proposal, where, among other things, we are thinking about using existing simulations and to create mock observations of some of these prolate structures and oblate disks and spheroids to ask, get another way to get a handle on the completeness problem, and to ask, are we being led astray by, as Avi said, surface brightness selection effects? So we're pursuing that. We're also thinking about the relative roles of baryons and dark matter. So we've gone into simulations like TNG50, which can marginally resolve the dynamics of these systems. And we've identified large numbers of high redshift, low mass, prolate, cigar-shaped or breadstick-shaped Milky Way progenitors. And we're now asking questions like, well, how abundant are they? What environments they live in? Are they actually in filaments? How are they oriented in the filaments? And can we do zoom resimulations so that we can actually then study the internal stellar dynamics, the orbit tracks of the star particles with higher resolution zoom simulations? And then finally, I'm the PI of a large NSF AAG program where we're developing next generation semi-analytic models for dwarf galaxies and satellites. And so as part of this, we definitely want to think about new analytic models for the prolate to oblate galaxy transition. So with that, I'll leave my summary up. I'll say I hope I've convinced you that this is an important puzzle. There's still lots of work that needs to be done. And I think the ELTs are going to be crucial, including the GMT developed here that Harvard is playing a big role in. And also theory is going to be absolutely essential. So I will stop there. Thank you, and I'll take questions.
Okay, thank you, Viraj, for an excellent talk. Do we have questions?
Hey, nice talk. I have two questions. Maybe I could just ask the first one. You said that you see no velocity gradient for one prolate galaxies, and you say it's because it's quite filamentary structures. And if you look at this kind of galaxies at different directions through the maybe the long axis, you should see a very point-like structures with very high velocity dispersion. Is there any other this kind of objects in your survey, and what's the fraction of this survey? So this.
Yeah. So great question. So we do see small circular objects in CEERS that are star forming, and we've quantified how many of those can be small star forming spheroids versus these prolate things seen down the barrel. And so I think we need follow-up work to look at like the dust attenuation in these small circular objects, which we expect to maybe be higher if you're looking down the barrel of a huge long thing. And maybe there's stuff with the surface brightness, the contours, the isophotes. So we have candidates, but we need to do more work on what these little round things are.
So in terms of a physical origin, actually more likely than anything else would be mergers, because they are much higher. They go like 1 plus z cubed roughly, the merger rate, and that's observed. So can you tell if we're dealing with components coming together just from the velocities?
Yeah, that's a great question. So I think this is another area where we're going to need the kinematic information along the face of these objects, because you're right, and I've definitely considered this also, that these edge-on looking things, I mean, these could be tidal features, which almost always are going to appear elongated in projection anyway, or they could be objects that, I mean, maybe you're seeing something, these objects maybe are, have purely radial motions, and maybe they are undergoing mergers preferentially along filaments. So I think there'll be exciting stuff. They're also cross-correlating with these upcoming Lyman alpha surveys, like by Chris Martin, with the Keck Cosmic Web Imager and the Keck Cosmic Reionization Mapper, where you can actually map out in Lyman alpha emission the filamentary structure at different redshift slices. So we want to cross-correlate.
But the merger would have two peaks in velocity of the two galaxies, whereas if it's a virialized system, you would have just velocity dispersion. I mean, right? So you can tell the difference.
Yeah. Yes, if we can get the data, if we can detect the
If you can
velocity.
put a slit that looks at the two halves, let's say.
Yeah. So we're doing that now with archival data. Surprised no one's done it. I mean, James did an amazing job, but they only targeted the biggest, brightest things. So. And they found one thing that's very strange. Right? It looks like an edge-on disk, but it's not.
If these were merging or mostly merging galaxies, the size distributions of the clumps be in conflict with any other observations or theoretical models of galaxy evolution? So they're obviously smaller than the entire system considered as a single galaxy. So does that affect things?
Yeah, that's a great question. There is a connection here with high redshift star-forming axisymmetric disks, which are observed to have these kiloparsec scale clumps, star-forming stellar clumps. Those are usually found in the more massive systems. So I think, we need more work with spectroscopy to figure out, are the clumps in these kinds of systems, in like my lower mass systems, how do they compare to the clumps in these more massive star-forming disks? And also, that might be another way to get at the kinematics question, because the clumps, we're doing this already. I don't think it's going to be definitive, but we're doing it, where some of these clumps are obviously going to be booming in H-alpha emission. So you can detect, you can talk about the gas kinematics of the clumps. How are they moving relative to each other? Are they rotating? Are they stationary? Are they radial motions along the major axis? So yeah, a lot of exciting things to do with clumps I'd love to talk about.
Thank you, Viraj. Great talk. I was wondering about, so you showed this bar chart diagram with the evolution of morphology. And and the fraction of this elongated galaxy is pretty high even at low redshifts, right? So I was wondering if the kinematics data is good enough at these distances to confirm this.
Yeah. So I've been talking to people about, as part of our Keck archival program that we want to do, but then also maybe getting new data with Magellan or Keck on some of these lower redshift things. So yes, that is definitely a fruitful thing. Like you see maybe in this case 40% or 20 to 40% prolate fractions at low redshift 0.5 to 1. You can definitely target these things to get stellar kinematics information. So I don't have constraints yet, but this is something that I think would be fruitful.
Okay, got it. And another question is, so this is all in rest frame optical, right?
Yes.
If you look at rest frame UV, does it change significantly? So there's like more disks and.
No. So that's one of the puzzles from HST in the mid 90s. These chain galaxies. They were defined in the rest frame UV, and we have now multi-wave. So we include that same imaging from Hubble ACS, right? And WIFC3. So we have multi-wavelength surface model parameters, axis ratios, spanning the rest UV to rest frame optical. And if we were to use the rest frame UV parameters for this kind of modeling, which we've done, the conclusions don't change. So still in the rest frame UV, you have lots and lots of these very elongated structures that we think might be intrinsically nearly prolate. But the rest UV is dangerous, as I mentioned, because it's a biased tracer. You're just looking at these star forming regions which might be distributed in a biased way compared to the underlying bulk of the stellar mass. So the fact that we're still seeing sort of rest frame optical with the improved sensitivity JWST is, I think, convincing, worth following up.
Hi, Viraj, really nice talk. I was wondering, so you said you'd found a number of examples of these kind of objects in TNG50, for example, as a cosmological simulation. I was wondering, firstly, do the abundances that you see in that kind of thing, if you just make a light cone image of TNG50 or something like that, does that match what you're observing? It's kind of...
So you're asking, like, are there enough of these objects in TNG50 compared to the data? So Annalisa Pilepic's 2019 paper itself actually plots the fraction of galaxies that are classified as prolate versus oblate versus spheroids in this mass redshift regime in TNG50. And the fractions are very low. They're 20% or lower compared to our 50% to 80%. But I've talked to Mark Vogelsberger and others, and the gravitational force softenings for these systems are of order, at these redshifts, are of order a few tenths of a kpc.
Yeah, it's pushing.
These systems are of, this is the 2 times the stellar half mass radius, roughly 1 to 2 kpc. So I don't know if I trust the dynamics of the stars and the shapes of these things. That's why we want to do zoom resimulations.
Yeah. Makes sense.
And then, when we have that, then we can do these kind of mock observations, insert these galaxies in different orientations and distances into the real JWST imaging, and ask, when do we start to be led astray?
Yeah.
Right. This is a disk, but it's really...
Yeah, the like slightly second follow-up to that is, I guess, if you haven't done zooms yet, is that if the ones that you have found in TNG50, have you looked at when they cease to be, the reasons why they become something else later on? Is it just emerges, presumably?
Yeah, that's a great question. We haven't looked in TNG50 yet. We've just finished identifying some of these candidates. But people have looked at this in the Vela simulations, which are high-resolution zooms. And the story is a little fuzzy, but there's processes, including mergers and gas inflows to the centers of these systems, that grows a substantial density of mass, maybe even a bulge. And if the orbits of the stars in these galaxies in the prolate or triaxial phase are passing arbitrarily through the center of the system, as opposed to being on nice circular orbits, then those orbits of the stars that pass near the center can be deflected by the growing mass density at the center of the system. And that can puff up the system, maybe make it more spheroidal, maybe disk-like. So exactly how that process happens, we need a lot more work on it, which is why I think this is exciting. So I'd love to talk more about this.
Thank you.
Great talk. I was wondering if these galaxies are mostly at the star-forming main sequence, or are they mostly like at their starburst phase? Because if they're truly like mergers, I think I would imagine like they would have enhanced recent star formation.
Great question. We had the same thought, and there's a figure in the paper where we compute and we plot the deviation from the star-forming main sequence for galaxies that we identify as being likely to be prolate versus oblate versus spheroidal. Relative to the star-forming main sequence at their respective redshifts, and we don't see any evidence yet of these elongated things being preferentially above the main sequence. They're all just scattered uniformly around the star-forming sequence for the redshifts. But this is where I think the spectra will be helpful, because we'll get better star formation rates from the H-alpha emission line, for example, compared to the star formation rates that we use, which come from the SED fitting, which are not as, I think, tight.
I was just curious, in the simulations, if you look at your breadsticks versus the pizzas, is there any difference in the dark matter halo shape?
Yeah, great question. So, yeah, there is. And the difference is that these elongated galaxies, they live in halos that are also elongated. So this has been known for 20 years, at least, that high redshift, low mass halos that are just forming tend to be prolate because they're forming along these filaments. So yeah, these galaxies live in, elongated galaxies live in elongated halos, and the entire system traces the dominant filament that it's in, that's dictating the accretion in a preferential direction. Which is why the intrinsic alignment paper that I wrote is so exciting, because you can actually test that with data from Roman. I wish you could do it with JWST and Hubble, but you can't, because the field of view is so tiny of these pencil beam surveys.
And then when do they become pizzas? Is it through tidal interactions or just mergers?
That's TBD, but I think it's something to do with mergers and central mass growth. Both from mergers, but also from cold gas accretion, maybe via filaments, that then enhances star formation at the center of these systems, and then maybe deflects some of the stellar particle orbits and puffs up the system. But how exactly it happens, it's TBD. There's some of these papers by the Vela simulation group that touch on this, but I think the proper comprehensive analysis has not been done.
Very interesting talk. So a follow-up question to what Ramesh asked. I think that maybe one way that you could potentially trace them down, whether that's a merger, tidal disruption, or anybody else, is like doing analysis for both the stars, dark matter, and gas. And if this is hard to do it from the observational perspective, we can get a lot of insight from cosmological simulations, because it could be that after you have those actually, kind of like basically disruptions and the stars get puffed up, maybe dark matter wouldn't do the same, or gas. So if you do it the same thing at the same time, you would at least get whether this is mergers or actually other things.
Yeah, which is why, we're definitely thinking about this stuff. So I'd love to talk more also, if you want to do some of this.
Oh yeah, of course.
One thing that you didn't mention, which could potentially have a small effect, is the weak lensing by shear.
Yes.
Do you want to? I mean, that will stretch images, but probably not enough, right?
Yes. So great question. And in fact, full disclosure, Avi and I have had discussions about this, and we started doing some calculations. So yeah, weak lensing could play some role. So strong lensing is definitely ruled out because the CEERS survey, for example, is selected to not have any major overdensities in the foreground. Weak lensing could have some role. We haven't finished the calculations yet, but for some of the highest redshift systems that we're looking at, you're almost guaranteed to fall within the virial radius of some massive low redshift foreground galaxy. So you'll have some lensing. I don't think it's going to explain the fact that we see, B over A of 0.3, 0.4, so on. But it's a very interesting calculation. And as a non-lensing expert, I am excited to learn more about that.
Hi, Viraj. Nice talk. There were, in the cutouts you showed, it looks like there were a lot of color variation within the objects and gradients or the different clumps. How does that play into these different interpretations of what could be causing objects?
Yeah, the clumps. So yeah, I mean, it's a puzzle. One is, okay, if you have all these clumpy galaxies, then that raises questions, is this thing, for example, here, is it dynamically stable? And if it's not dynamically stable, then is it accurate to say that this thing, is some kind of prolate ellipsoid? I had a meeting with David Spergel on Monday, and we were talking about this, looking at the Hubble Atlas from 1961, where you have all these E6s and E7s in the local universe. And those are heavily flattened, but they're also very smooth. So they're dynamically settled, relaxed systems. Now it helps us because some of these clumps probably will be bright in emission lines, so we can go in and look at the gas kinematics and ionization and stuff. Color gradients are also very important. So we are actually going in, so with a grad student at Yale, Harrison Suchero, who's just starting a pre-doctoral fellowship at the CCA, we are going in and doing these isophotal fits to get surface brightness profiles in different bands. And then that might be a way to say, in addition to like isophotal twists and stuff, we'll have surface brightness profiles in different bands. Then that's color gradient, you can get color gradients. And then you can play the games, which will never be definitive, but you can play the games that, okay, well, if this thing has a redder center, maybe it's a disk with a bulge. So sure, but I want the spectra with GMT at some point.
Hi, you were excited to get out of the rest frame UV and into the rest frame optical. 30 years ago, we were just as excited to get out of the rest frame optical and into the rest frame infrared with the low redshift things. And one of the reasons was because at rest frame V, something like our local galaxy, that's the cigar galaxy, M82, has 30 magnitudes of extinction at V still to the nucleus. So I just was curious, how much do you think you understand the extinction to these things in the different models of breadstick versus edge on disk?
Great question. I wish we could do rest frame infrared for these things at these high redshifts, but we don't have anything with the resolution. Yeah. Maybe one of NASA's next great observatories, the Origins telescope, might be able to do something. I doubt it. But yeah, there's more work that you can do. So in our 3D shape modeling, where we have these different kinds of 3D ellipsoids that we then create these B over A versus size probability maps, right? This all assumes, transparent ellipsoids, no dust attenuation. But there are ways to forward model, add a parameter for dust attenuation, and also ask, well, what if the dust is clumpy on small scales versus what if it's uniformly filling throughout the volume of these ellipsoids, and how would that change? Would you still get a banana for a prolate ellipsoid if it had, dust in it? I don't know the answer, but that's part of actually our JWST legacy proposal. So that'll be nice to do.
Yeah, and the other thing you'll want to think about is an apples to apples mass comparison. So the stellar mass, how much could that affect your estimate of the stellar mass when you're trying to compare the different shaped galaxies with similar stellar mass?
Yeah, that's a good point. Yeah. The other weird thing, is that these galaxies are at early times. So, I mean, the stars in them are a few billion years at the oldest, So it's very different from looking at the rest frame near infrared for local local galaxies to probe the bulk of the stellar mass from 10 billion-year-old stars. So yeah, I'm kind of thinking that through. So.
Me again. Do you have any idea about the environment that these things are in observations? Because I'm trying to think of theoretical explanations. It would be useful to know if they're vaguely near larger structures or whether they're just vibing by themselves somewhere.
Yeah, so as part of my 2019 paper, we computed pair statistics and different measures of environment, and these things are relatively isolated. They do, in many cases, tend to have some other nearby elongated system in projection, but I think we'll need Roman for this, where we get the large field of view.
All right, we are just about at time, so I think we will wrap up here. Let's all thank Viraj again. Thanks, everyone.
Very nice to meet you in person.
See you.
Yes, 2:30. And also lunch. And
If you want to visit a few minutes early, I can do a meeting at 2:30 in my office.
I might have a meeting, but yes.
If you have, you can come back.
I think your comment about stars being on radial orbits and getting